Okay, so examples now that are really, that are directly in your notes, and kind of jump around a bit here to this idea of limits. And the thing that I want to stress from that very first video is that a limit describes the behavior of a function near a point. Okay, it's not exactly what's happening at the point; it's happening what's close to the point. Okay, and sometimes trying to block out or ignoring the actual behavior because it might be distracting is really helpful. And so I'm going to draw in. I think there we go. I'm going to draw in just almost like just like a vertical line here. I guess I don't know this. To try to maybe help block the behavior. So if I want to know like what's happening as we approach 17, I can ignore the actual behavior. Or if I can kind of block out what's happening as we approach 6, I don't want to be distracted by the jump, because remember, a limit is what should have happened. What does it look like as the left and the right come together? Okay, so now, like a piecewise function, it looks very sinusoidal at parts, and there's linear parts, and there's a jump and things like that. So that's kind of cool. And then I redrew it down here only because I wanted to make reference to that. Okay, so it says limit as x approaches 0. Remember, so x is approaching 0, so you could kind of block this out, and I don't want to be distracted on what's really happening at 0. But I want to know what's happening as I get close to 0. And this is where I wish you could see, because I'm going to be drawing like little arrows from both sides. And I want to know, is the behavior from both sides, actually I want to separate those two, sorry. Cut that out. Oh, I copied it. That was nice. Cut. There we go. I want to notice, is it behaving the same way from both sides? So I'm going to pick yellow. That's fine. There we go. Line style. Perfect. Okay. So going from this side, and then hopefully it'll separate from that side. Okay. It didn't, but that's okay. So is the behavior the same? Yeah, they're both approaching 16. So I know that the limit is equal to 16. And you might say, well, that's not that hard, Mr. Brown. That's what the value was. I'm like, yeah, that's true. Sometimes if there's a very smooth function, if there's nothing strange happening, there's no jumps or asymptotes or discontinuities, then limits are boring, right? Like limits explain what happens. Like limits explain what should happen. So if what's supposed to happen happens, then there's no weird difference there. Okay. Now, -10 from a positive sign. And now this is the first time we've seen this. So if I first go over here to -10, I'm noticing that there's definitely a disparity. Like from the left, versus from the right, there are two different y values. And so right now these aren't meeting up. So like this right here, like they're not approaching the same value from the same side. So I know that like there's an issue here. But this limit focuses just approaching it, if you look here from the positive, just from the plus side, which means from the right. So I want to make sure I know that that means from the right, and only from the right. Only from the right. So from the right side. So only from the right side. So the right side, what's right, the right side of it. So, and here's where sometimes students make a mistake. It's from the right, but you're moving at it left, right? You're coming from the right. So I'm coming from the right. Get this out of the way. I'm coming from the right. Go back to pen. I'm coming from the right, but my direction is moving left, but I'm approaching it from the right and only the right. And so what is the y behavior from the right? The y behavior is 12. But now when you look at the next problem, it says approach -10 from the negative side, or from the left. So approaching it from the left side, we'll go, I guess, blue, sure. So we're only approaching it from the left side. So just the left side, just this side. And again, it's from the left. So it's from the left, but the particle, or we're looking at it as we move right, but it's from the left. So I should probably only from the left. So that's how I can distinguish what direction. From the left, the y values are getting close to 19. It doesn't matter that there's a hole there. It doesn't matter what the behavior is at that actual point. Because if you remember, a limit is asking what's happening as you get close to the point, not what's happening at the point. So as I get close to negative 10 from the left side, it's a linear function. The y values are getting closer and closer to 19. Pen, there we go. So we say it's 19. Now, if it doesn't specify, and here's where the fun begins, right? If it doesn't specify, and it just says negative 10, it doesn't say which side, it doesn't say left, it doesn't say right. That means you have to do both. That means you have to make sure both sides approach the same value. And so if I'm looking at the left and the right, well, one side is 12, one side is 19. Okay, you can't be in both spots at once. This is where in class I talk about like Harry Potter and splinching yourself. Poor Ron Weasley, right? When he's going to the Forest of Dean, and half of him, or most of him, I should say, ends up there, but part of him doesn't. Right? You get splinched. That's painful. Okay, limits kind of work the same way. I know that's a stretch, but I hope you enjoyed that little analogy. You can't be in two places at once. It's one or the other. So if one side approaches 12 and one side approaches 19, then together they, like, if I ask what's the limit in general, no, it doesn't exist. Okay, it does not exist. And this is where I'm super sad that I can't show this year. But maybe you're a fan of one of the greatest movies of all time, Mean Girls, because in Mean Girls, the very end of the math competition, Katie Heron shouts out, "The limit doesn't exist," for this very reason. The left side doesn't approach the right. So just a fantastic acting job by Lindsay Lohan. All right, good job. But I am sad that slightly because I can't share my passion of Mean Girls directly in class. Okay, tear to the eye, moving on. Limit as x approaches 23. So now I'm going to look at my graph at 23, which is an endpoint. And so 23 is filled in, even though it doesn't really matter, though, because I'm blocking that out. So the behavior from the left as we get close to 23 is negative 2. But the thing is, we have no idea what's happening to the right of it. And because we don't know the behavior to the right, I cannot claim what this limit is, because for this limit to exist, the left side and the right side have to join together. So the left side is approaching negative 2, the right side is approaching who knows what, I don't know. So therefore, this limit is another, does not exist. There we go. So it does not exist. So it's up to you. If you feel like you're starting to get the hang of this, feel free to pause the video, fill this table out, and then play the video and see. Because I'm just going to walk through each of these next examples. Okay. I'm going to have to move my graph over though for number 6. Now it says, let's approach 23 from just the left. Okay. So now I'm indicating I don't, like just the left side. I don't need this, just the left side. Okay. So move this over here and move this over there. Cool. All right, there you go. So now just from the left, I'm good, because just from the left, I hit right at negative 2. I don't need to worry about anything else being over here on the other side. So this is defined. This is fine. I can actually take the limit, and the limit is equal to 20, as x approaches 23 from the left was equal to, there it is, negative 2. Okay, as x approaches 6. Okay, so again, don't let the behavior of the function actually distract you. I see there's a value of 6 up here, 20, and 6, 12. What do I pick? I pick the one that when I look from the left and I look from the right, are the y values getting closer and closer, converging on a point? They are, and it's 12. And so the value of the limit is equal to 12. Now, what's this guy up here? If I looked up there at that point and I see, oh, look, there's a point to find up there. Oops, my bad. Yeah, that's okay. That's the function point. The function point doesn't always have to equal the limit point. So the limit point was 12. I don't care about the function point. Remember, a limit just wants to know what should have happened. There shouldn't be this weird jump here, right? That shouldn't have happened. It should just be a filled in dot. So the limit value is 12. And again, thinking about limits are going to allow us to sort of fix holes in graphs. And that's really where we're going with this. Any of these point discontinuities that might give us an issue when we try to graph them, or they might give us a 0 in the denominator, we're going to be able to kind of rectify the situation by taking a limit as opposed to looking at the function value. Okay, negative 20 from the right. So here's negative 20. And remember, this positive sign, oops, my bad. This positive sign here, there it is, just from the right, remember, from the right. So I'm going just from the right. So from the right, from the right, from the right, negative 20, and it approaches negative 5. The behavior or the y value, they're getting closer and closer to negative 5. Okay? As we approach 10. So there's nothing up here. There's no plus or minus, so I need both sides. So as x approaches 10, well, 10 is nowhere defined like as a point, but 10 is defined in this horizontal segment. So, it's somewhere here, but everything around it, all the values as I approach from the right, all the values as I approach on the left is very boring. They are all equal to 12. 10. Excellent. Okay. As x approaches 14. And then let's see, x is approaching, well, okay, same thing, right? It's just further down the road. So that's also equal to 12, which is great. Okay, now sometimes you might have to provide your own piecewise function, and I don't think it'd be as complicated as that graph. But and the next one, example 11, says sketch this graph first, and then start looking at these limits. So let's sketch that. I mean, these aren't super hard functions to graph, but it may have been a while since we've done a piecewise function. So negative x plus 1. So that's a linear function that has an intercept of 1 and has a slope of negative 1. So if I wanted the whole graph of negative x plus 1, it would look like that. But remember, we only want this graph when it's less than 0. So we only want that graph like over here, like this region. Like that's when x is less than 0. And it's strictly open-ended, right? So what I'm going to do is I'm going to graph just, maybe if I can try. Well, let me do it. Trying to erase just that part. Oh, there it is. Okay. So we're just wanting that part right there. So I'll go to the pen. Maybe I'll pick a different color. Green sounds great. And so here, and going off in this direction. Now, this point is 0, 1. It's an open dot, but sometimes open dots are okay for limits. Okay, now x minus 3 if x is greater than 0. So I'm going to go to intercept of negative 3. 1, 2, 3. And this has a slope of 1. So it's going to look something like this, but it's only when x is greater than 0. So again, open dot. And I'm going to go off in this direction. Okay, so I can already see there's an issue here, right? This is 0, negative 3. And then our very last one says be the number 6 when x is 0. So for one instant, when x is 0, we want to graph 6. So 1, 2, 3, 4, 5, 6 up here. There's the point 0, 6. Now, that's the only one that's filled in. That's the one that I would refer to as the function value. So right here is the function value. And sometimes I'm asking about that, but when I'm doing limits, remember, I don't really care about the function value as much as I care about the behavior as we get closer and closer to a particular point. Okay, now, maybe I'll just use this nice little red segment bar here. Oh, that's very thick. Okay, so that didn't, that wasn't what I was thinking about. Let's try again. Oh, cool. Okay, let's go one more thicker. Sorry, I'm just playing around with this. That looks nice. Okay, so I don't need this and I don't need that, but this is nice. Okay, so it says x approaches 7. So 7's over here. And again, remember, I'm looking at the behavior from the left, from the right. There's really nothing suspicious going on. It looks like it should follow the behavior of this function here. Now, this function, is right here. So it's x minus 3. So the behavior there should be 4. And so when nothing like suspicious happens and you aren't given a particular point but just an equation, like when nothing suspicious happens, that means the function's going to obey what should happen. You could just put in that value. And sometimes a direct substitution is a strategy to find a limit when nothing weird is happening, or no jumps or asymptotes or holes. Okay, now it gets a little more interesting. 0 from the right. So now when I approach 0, maybe I do need this one, right? Hey, what's happening? Blackout. Okay, 0 from the right. So we're coming down here from the right. Remember, we're moving in a left direction, but we're coming from the right. This is where our prepositions are so important. From the right to the left, but it's from the right. So from the right, the y values are getting closer to -3. So then I'd say that that limit value is equal to -3. Go to green, why not? Okay. Now from the left, so now I'm approaching them from the left. So from the left. So it looks like they're approaching the value of just 1. Oops. Pardon. And then here, it's both sides, both the left and the right. And so graphically, I can see the left side and the right side aren't meeting up. Numerically, I can see the left side and the right side are meeting up. So that limit does not exist. Sometimes students ask, could you just take the average, right? And if you're thinking about that, that's probably an okay thought to have right now. Could you average the two, halfway between -3 and 1, to get like -1? But the thing is that a limit has to describe the behavior at the next point. In other words, it has to be like there, and there's no distance in between points. Like points are a unitless, dimensionless object. So like there's no concept of length, and so like what's right next to that point has to fall into a sequence, and a jump indicates that you're covering distance, and so you don't take the average. You have to make sure you're right next door, so to speak. So good thought, okay thought to have right now, but at this point, you kind of have to realize that nope, it has to be left and right exactly equaling the same. Okay, so I want to stop the video because you guys have been looking at those a lot. I'm going to do another graph example and then do some stuff on our calculator.